All right, so actually I think I want to show one more thing before we move on. Remember, whenever you're doing any kind of problem, it's a good idea to have the process on some kind of a property plot, just showing you what sort of process is occurring, especially if you're dealing with some kind of mixtures. So let's put up the TV diagram up. So here's TV. Let's put this up one more time. So here's the specific volume. There's a dome. So here's the isobar. This is pressure, 1.5 bar. Okay? State 1 was a saturated liquid. And then we moved to state 2, which is some sort of mixture. Okay? Now, you could also draw the TS, specific entropy diagram, and it would look qualitatively the same. S, specific entropy, is a property like specific volume. The saturation dome looks the same for specific entropy. You have a saturated liquid over here, a saturated vapor, the critical point. Everything still applies for the TS diagram as for the TV diagram, okay? And the isobars here, again, are upward sloping outside of the dome. So P equals 1.5 bar. So we started off with a saturated liquid with a specific entropy S1. I don't remember what that was. And then we moved over to state 2 and ended up with a specific entropy at state 2. So this is our change in specific entropy. So that's what the process looks like on a TS diagram, where S is specific entropy of the system. The dome looks exactly the same, qualitatively the same as the TV diagram, okay? So I do want to point that out. As we do these problems, we're going to start putting up TS diagrams as opposed to TV or PV diagrams so that we can keep track of the processes. All right, let's switch gears here and try to figure out some general equations that allow us to calculate the change in entropy of some system. We've been using tables so far in this example because we had a saturated mixture. We had to use saturation tables to calculate entropy of the system at the initial and the final state. It'd be nice to derive some equations similar to the DH and the DU property relationships so we can quickly calculate change in entropy without having to use tables, or at least use tables as much. Okay? So the TDS equations. Temperature ds property relationships. TDS property relationships or equations. That's what we're going to derive here next. Okay, let me start off with a system. And this system moves from state 1 to state 2. Okay, state 1 to state 2. Now, this process is going to be a differential process. So I'm going to start off at state 1, and I'm going to move a small distance. A small distance is going to be a differential process to state 2. So this could be a property. This is some property 1, and this is some property 2. Okay? It could be temperature, volume, entropy, internal energy, whatever. Now I'm going to put a constraint initially on this process. I'm going to say the process, I'm going to constrain constraints. I'm going to put some constraints on this process, 1 to 2. First of all, this process is going to be reversible. It's going to be reversible. So we're going to go from state 1 to state 2, and we're going to do it reversibly. I'm also going to assume or impose the constraint that any work that occurs is boundary work. So work equals work boundary work, as I go from state 1 to state 2. I'm also going to say that any heat being added to my system as I go from state 1 to state 2. So I'm going to add a differential amount of heat. This is a differential process. Add a differential amount of heat. That the interaction temperature is equal to the temperature of the system. So the T interaction is equal to the temperature of the system. Now, that actually falls from the reversible process. If the temperature here at the surface of my system was not the temperature of the system itself, then as the heat flowed into the system, it would flow across a temperature difference. And heat transfer across a temperature difference is irreversible. So I'm going to point out that temperature, the interaction temperature, is equal to T, and I'm going to write here reversible heat transfer. Because it's a reversible process, any heat transfer process needs to be reversible. So the interaction temperature has to equal the temperature of the system. So here's the temperature of the system. There's the temperature at the surface of the system where the heat transfer flows across the system boundary. These temperatures better be the same, else we have heat transfer as it flows into the system, the heat flows into the system. We would have heat transfer across a finite temperature difference, and that would be irreversible. So those temperatures must be the same, okay? We're also going to neglect changes in kinetic and potential energy. So dPe is equal to dKe, and that's also going to be equal to 0, all right? Okay, so let's write the energy balance for my system. This is a closed system. Let's write the energy balance, and let's write the entropy balance for this differential process. So we have the differential energy balance, del Q minus del W bound is equal to dE, which is equal to du. Okay, why is D equal to du? Because we're neglecting changes in kinetic and potential energy. So this implies del Q, oh, by the way, what's differential boundary work? It's PdV. So this is actually PdV. PdV. So I get del Q minus PdV is equal to du. All right? Let's write the entropy balance. ds is equal to del Q over T interaction plus del S gen. That's the entropy balance for a closed system. That's the entropy balance. So this is the E balance. E balance for a differential process, and this is the S balance. Now this is a reversible process, so what's del S gen? 0. Reversible. What's the interaction temperature? Well, I've already assumed, since it's reversible heat transfer, I've assumed that this temperature, the interaction temperature, is T. So I get ds is equal to del Q over T. Now I'm going to solve that ds equation. I'm going to solve it for the heat transfer. Del Q del Q is equal to T ds. All right? Now I'm going to substitute that into my energy balance. So this is T ds. So I get the following. T ds minus P dV is equal to du. Let's take the P dV and put it over on the other side of the equation. And I get TdS, temperature times the differential change in entropy, is equal to P dV. Actually, I'll put du first. du plus P dV. du plus P dV. So let me write that equation down over here. Just going to write that down over here so we can keep track of it. T ds equals du plus P dV. Okay? Now, before we get too excited, I want to point out that this equation, we had a bunch of restrictions here. Primarily that the work was boundary work and the process is reversible. Well, guess what? Entropy is a property, so its change is path independent. It's a point function. This equation, TdS is equal to du PdV. Everything in here is a property. They're all point functions. So this equation is valid regardless of path. So I'm going to write right over here, valid regardless of path or general. So I'm going to write valid for any path or process. Any path or process. Reversible, irreversible, work is boundary work, work isn't boundary work, who cares? Everything in that equation is a property. So it's changed, these changes are path independent, okay? Now why did I put this weird curly bracket here? Because there's actually two versions of the TdS equation. I could have, we have a du plus PdV in here. I could have written this in terms of enthalpy instead, dH. Let's see here, H is equal to U plus PV. So dH, let's see here, dH so we have H is U plus PV. So dH is equal to du plus, I got to use the chain rule here, PdV plus VdP. So I could solve that equation, I could substitute that equation into that equation, du plus PdV. So du plus PdV is equal to dH minus VdP. So I could substitute this right into here, and I get the second TdS equation. The second TdS equation. dH minus VdP. Put a box around this. This is the TdS property relationships, and they allow us to relate changes in entropy to changes in internal energy, enthalpy, pressure, and volume of the system. Put a big box around this. This is valid anywhere, in the dome, outside of the dome, superheated vapor, supercooled liquid. This equation is true for any process, anywhere between for a differential process. So put a big box around this. Let's take a little break here and we'll reduce it down to other versions.